Well, in this video we are doing the derivative of inverse trigonometric functions examples. If you want to see the proof of where these results came from, I'll link the previous video in the description, but we're just going to be using those results to work out some problems. So let's get started. Okay, let's go. First example, differentiate inverse tan x over 4. Now, from our last video, we might have been able to find the derivative of this. If I have it in the form x over a is a over a squared plus x squared. Now that's going to be the easier way to do this one, because if I look at that, my a is just 4. So the derivative here, dy dx, will be a, which is 4, over a squared, which is 16, plus x squared. So we're already done. That's easy. But on our reference sheet, so if you can't remember this, then on our reference sheet we have d dx of inverse tan of a function of x. Okay, and the result that we have there is the derivative of that function over the function squared plus 1. And if we were to do that, we would get, well, what's the derivative of x over 4? That's a quarter over x over 4 squared plus 1. Now, obviously it looks pretty different. You should be able to simplify this into this, but the first option is a lot easier, so stick with that. And yeah, make your life easier. Okay, second example is differentiate inverse sine 2x. Now, very similar to the first example that we just did. We have two options that we can use. We can use the derivative of inverse sine if we have a function of x. In this case, our function of x is 2x. That will be our f of x. And our derivative on our reference sheet is the derivative of that function over root 1 minus that function squared. Or, if it's in the form inverse sine x over a, then it can be 1 over root a squared minus x squared. So we actually had the same sort of decision to make in the last one. In the last example, the second option here was the easier one. But in this example, the first option is going to be a bit easier, because the derivative, if f of x is 2x, then f dash x, the derivative of f of x, is 2. So the first option is going to be the easier one. So dy dx is 2 over root 1 minus 2x squared. Now that's 2x all squared, so it's 2 over root 1 minus 4x squared. Okay, so if you wanted to have a look at that second option, you can use it. If you want to use the second option, then your a, because it's 2x, your a would actually be 1/2. So have a look at that, but it's going to be a bit more simplifying. So first option is easier in this one. In the previous example, we used the second option. Differentiate e to the power of inverse cosine x. So hopefully you guys recognize this one as a chain rule. So we have a function of x in our exponential function. So a function of a function is our chain rule. So we want to start by, we want to let u equal inverse cosine x, and then our y is e to the u, because we know that one's really easy. It's e to the u. For the derivative, the derivative of u with respect to x is negative 1 over 1 minus x squared. Straight off our reference sheet that we proved in the last video. And then our chain rule, we're multiplying those two together. So dy dx will be negative 1 over root 1 minus x squared times e to the u, but I don't want u, I want this in terms of x. I'm going to sub in what I know u is, which is inverse cosine x, and then we get our final answer. Let's just simplify this a little bit. All over 1 minus x squared. Let's look at this example. Differentiate inverse sine x over 3 plus 1. So remember what's on our reference sheet. We know that dy dx is derivative of that function of x, root 1 minus f of x squared. Now we want to use this one because here this is our f of x, okay, because we have inverse sine of a function of x. So our dy dx will be, well, what is the derivative of x over 3 plus 1? The derivative of that is 1/3. So we'll put 1/3 over root 1 minus, and it's going to be x over 3 plus 1 squared. Okay, so just using our formula there, but looks pretty ugly. So let's do some simplifying here. So 1/3 over root 1 minus, this is a perfect square, so it's going to be x squared over 9 plus it'll be 2x over 3 plus 1. Okay, so let's put that in the middle there. So it's a bit better. Okay, now it's minus all of this here, so the ones will cancel, and I can write this as 1 over 3 root minus x squared over 9. And if I want to get a common denominator, then this number I can times by 3 over 3, so I'll end up with 6x over 9. And then root 9 is 3, so that's actually, these are going to cancel here. That, and that will cancel. So final answer will be 1 over root 6x minus x squared, and we're done. Last example for today, let's find the gradient of the tangent and normal to the function f of x is inverse sine x all squared when x is 1/2. So for this one, I really want you to recognize that we have a chain rule here. We have the inverse of sine within that square function, so we have a function within a function. We want to let u be inverse sine x, and u dash will be 1 over root 1 minus x squared. That means our y is u squared, and the derivative of that is 2u. So because it's a chain rule, we multiply those two together, so we get 2 inverse sine x over root 1 minus x squared. Okay, so we want to find the value of the derivative at 1/2. Okay, so inverse sine of 1/2 is pi on 6. So 2 times that will be pi on 3 over root 1 minus a half squared. Half squared is a quarter, so 1 minus a quarter is 3/4. And just simplifying things a little bit there, and we get 2 pi over 3 root 3. Okay, so that means the gradient of our tangent will of course have the same gradient, so 2 pi over 3 root 3, and the gradient of our normal will be the negative reciprocal, so negative 3 root 3 over 2 pi. And that's it for today, some examples of how we can find the derivative of inverse trigonometric functions. So hopefully you find the video useful. If you could hit the sub and smash that like button, I'll see you in the next vid.